Okay, and 0 degrees Celsius, right? Or if we can convert that to Kelvin, that will be 273 degrees Kelvin, right? So scientists have made this. This is kind of their standard. So our gas is going to behave the most ideally at this baseline. So gases obviously can be hotter than this. Hey guys, give me just a second. My son is. Okay, so remember, we wanted gases to be hot. The hotter the gas, the more likely it is to behave ideally. So this is our base temperature for when gases start to behave ideally. So if it's hotter than 0 degrees Celsius, and I know this seems innately cold to us because this is the freezing point of water, and we think, hey, that's cold. But in the terms of gases, that's really not that cold because gases freeze at a way lower temperature than this. They're normally gases, like the oxygen that we're breathing is boiling oxygen, right? So gases that are hotter than 0 degrees are considered ideal, right? So it can be hotter than that. So this is our baseline temperature for when they start to behave ideally. The same for our pressure. We can have gases that are at a lower pressure than 1 atmosphere behave ideally. This is our baseline, right? So we want a gas in terms of ideal conditions lower than 1 atmosphere or hotter than 0 degrees Celsius. But anytime you see STP, like in some of the problems that we're going to be working, that because you might read some of those problems and start working it and think, hey, I don't have enough known variables to be able to solve this problem. But you know 2 variables right off the top just from seeing this word STP. You know what the pressure is and you know what the temperature is. So don't let that confuse you or let you trip you up. That is going to be there in those problems. Okay, so let's look at concept check question 5. So we've got concept check question 5. Let's let Ainsley Kate in. Welcome, welcome. So we are doing concept check question 5 right now. So you're given some scenarios and you want to pick the gas that's going to be the most perfect. We want to pick the straight A student gas, right? So if we look, our first one, we have 1 mole of gas at 275 Kelvin or 1 mole at 350 Kelvin, right? So remember, ideal gases behave the most perfect when they are at higher temperatures. So which one are we going to pick to be our ideal gas? The one at the higher temperature, right? So that would be our one that was at 350 Kelvin. Okay, our next one has to do with pressure. So let's go ahead and circle this one. Pressure is the opposite of temperature, right? So our gases that are the most ideal are going to be at the lowest pressure. So if we have 1 mole of gas at 740 torr and 1 mole of gas at twice that pressure, 1500 torr, the one that is at the lower pressure is going to be the one that is going to behave the most ideal because there's nothing forcing those particles of gas together. They occupy the least amount of space. Therefore, they are able to behave the most perfect in the gas world, right? So let's look at the next one. So our next one has to do with the container. So we have the same amount of gas. One is crammed into a small container and one is in a large container. We want the one that's going to have the least amount of pressure. So the least pressurized gas is going to be the gas that is in the larger of the container. And be sure if you guys have questions about these as we work through them, because we're going to be working on lots of problems together today, please unmute your mic, ask a question, whatever. I'm here to help you guys. So I know we're going real fast today. Don't be scared to stop me and ask a question. Okay. So our last one has to do with the size of those gas particles. So we've got just some hydrogen gas, and then we've got this bad boy, C12H4Cl4O2. So this bad boy has lots of things in there. I see some chlorine and some oxygen. So by now we've learned a lot about chlorine and oxygen. They're really electronegative. That means they have a partial negative charge. So this molecule is most likely polar. So not only that, it's got a whole bunch of atoms in it. This thing is massive if we're talking about size of this molecule. It's our Big Mac truck on the highway where our hydrogen gas is a little dude on the motorcycle, right? So looking at terms of ideal gas, we want particles that are smaller. The most ideal gases take up the least amount of space and are the least polar. So if we're looking at this molecule, our smaller one, the least polar one, is going to be the most perfect one. It's going to be our ideal specimen. So it's going to be our most ideal gas. So questions about any of those little topics? Okay, Janie, we'll get you back in.
Can you hear me?
Yeah, I can hear you.
Okay. Janie couldn't hear you. That's why she just left, and her mic still isn't working. So she's trying to figure that out.
Oh, okay. I wonder. I don't know if it's anything I can do on my end. Let me see if I can unmute her. No, I can't touch it. No. Well, Janie, if it keeps it working, just kind of log off, and I will be sure that I put up a video of class, and hopefully you can hear me on the video recording. Sorry about that. I really don't know how to fix it. I've updated my computer, and I've done all that I know how to do. So, can you hear me? I see
Yes,
you.
ma'am.
Yay! Okay. Great. That makes me so happy. Okay. Any questions so far about gases? Ideal gases, we're ready to do some math. Yay! Okay. So, how we practically, oh, thank you, Levi. How we practically use this, right? So we have our ideal gas law. This relates all the variables that we're concerned about of a gas. So we've got P, V, N, R, and T. So P is pressure, V is volume, R is a constant that you'll have to know. It is 0.021, and we'll talk about the units here in a minute because they're important. We've got N is going to be our number of moles, right? So it's our amount of particles. And then we have temperature. So those are the four variables of a gas that deal with our ideal gas law parameters, if you will. Pressure, volume, number of moles, and temperature. So they're all related. You'll notice that this gas law is different than Boyle's law, Charles's law, and those things from the beginning of the chapter. Those laws had to deal with changing conditions, right? So if I change the pressure, how does the temperature respond to that? So in those problems, there is a clear before and after, where our pressure changes, our volume changes, our temperature changes. When we're talking about the ideal gas law, you'll notice there's no before and after. This is at one given instance in time, how all of these variables are related. So if you read a problem and there's like before conditions and after conditions where our temperature changes or blah, 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 you know, you're not going to really need to use our ideal gas law. It's probably going to be a Boyle's law or a Charles's law question. Now, you might have to use the ideal gas law to find one of those variables for the beginning and one for the end. But just it's good to know that our ideal gas law has to be under a set one snapshot in time, right? So if we look at our ideal gas law constant, this big R, you'll see it has some crazy units to it. But those units are a guide for us because they tell us what unit our other variables have to be measured in. So if we look at our unit here, it's a liter. And so liter would be our volume. So our volume has to be in liters when we plug it into our ideal gas law. So if we're given a volume in milliliters, we would have to convert that to liters before we can do the math. Otherwise, our math is going to be off, right? So our unit for pressure has to be an atmosphere. So if we were given pressure in, say, torr, we would have to do the conversion and get that into atmospheres before we could plug in and do the algebra to solve for our unknown variable. Okay, N is a mole, and you'll see that in our ideal gas law under here. So the mole is on the bottom. And then our temperature has to be in Kelvin. So if you're given your temperature in Fahrenheit or Celsius, you've got to convert it to Kelvin before you can do the ideal gas law. All right. So be sure you're aware of that. Also, where these units are, tell us how they relate to each other. Remember, when we talked about Boyle's law and Charles's law, we talked about a direct relationship and an indirect relationship. So where they're at on this side of the fraction tells us how those variables are related. Just kind of a tidbit. Okay, so the most important thing that you can know practically for this is the units that all your variables have to be in, because that's the most 100% the most common mistake you're going to make. You're going to do the problem, you're going to plug everything in the correct order, you're going to do the algebra right, but you forgot to convert milliliters to liters before you did it, so your answer is going to be off by 3 decimal places, right? So that's the frustrating part when we're dealing with gases. It's one of the other frustrating parts of chemistry. We have to be so particular about how our measurements are used in our algebra. Okay, so question so far. We're ready to work a problem. Great. So these are word problems. Don't let them scare you, right? Half of the battle is understanding the words and taking away what's important out of the question so we can get started. So we're going to look at concept check question 6. I've got it written out here for us. Let's see. This way. Okay. So concept check question 6. Flip to it so I don't have to read it. A sample of gas contains 18.45 moles at STP. What volume does it occupy? So this is a problem. So I read this. Important things for me to note. Any numbers, right? I also see this STP, right? That should be something important. So practically, if I'm working this problem, I'm going to underline all of the important things. So for me, when I read this, I automatically know 18.45 moles is important, STP is important, and volume is important, right? Volume is important because that's what I'm trying to solve. I'm trying to solve for big V. I know STP means that I know what the pressure is and what the temperature is. It's 1 atmosphere and 0 degrees Celsius. That's 18.45 moles for me is an N, right? Because we're looking at, since it said STP, this is a gas. Automatically, I should know I'm going to need my ideal gas law. PV equals NRT. So from this problem, I'm going to have to find each of these variables except the V, because the V is what I'm trying to solve for, right? So if I look up here, my pressure is, since it's an STP, my pressure is 1. I don't know my volume. That's my unknown. The volume is what I'm trying to solve for. I know my N is my number of moles. That's given to me in my problem, 18.45. R is a constant, so I can look that up or have it memorized. You're taking your test. I'm perfectly okay with you writing what R equals at the top of your paper, right? It gets kind of silly for you to have to memorize it because it's always going to be given to you. And I know temperature, since it's at STP, that temperature is 0 degrees Celsius, right? But I remember that since I'm using the ideal gas law, my units for all of those things are determined by my constant, by R. And R tells me that my pressure has to be in atmospheres, my volume has to be in liters, and my temperature has to be in Kelvin, right? So before I start doing my algebra, I have to make sure I convert each of my variables into those units for R. So here we go. We've got PV equals nRT, and I've gone through and I've written out what my problem gave me, what I knew to be true. So I knew in this problem that my pressure was 1 atmosphere because it's at STP. I don't know my V, that's what I'm solving for, that's why I circled it. I know my N is 18.45. I know my R, you can hardly see that because I did it in orange. It's 0.0821. Okay. And I know that my temperature was 0 degrees Celsius, but that's one of the most easy conversions ever, because if it's in degrees Celsius, all we have to do is add 273 to it to get its temperature in K. So 0 plus 273 equals 273, right? So since I know all these things to be true, all I have to do is plug them into my equation and solve for what I don't know. So then it just becomes a really simple algebra problem, right? And you can see that at the bottom. So 1 atmosphere times my volume is equal to my number of moles times my gas constant times my temperature. And when I do all that, I should get something pretty close to 414 liters. I will say too, several of these problems, the way your textbook rounds them, since they use significant figures, they round at each step of the problem. And if you're like me and you like to do the problem out and then just do math one time, your answer is actually more accurate than the textbook, because the textbook rounds more than you do. So it's okay if your answer is off by a little bit of rounding, as long as you look and you work the problem the same, right? Because I think your textbook has a different answer than this. Ours is rounded a little differently. So questions? Problem's actually pretty simple once you sort through and you know, hey, I've got to look for all these variables in my problem, and then I can just algebra it, and hopefully you can get the right answer. Okay. Cool. So we've got one more that works with our ideal gas law, and that is number 7. So we're going to do the same kind of strategy here. We're going to look at our problem, and we're going to try to circle or star or write out any of the important information. So if you're looking in your textbook, I've just written out concept check question 7. A sample of gas that contains 12.5 moles is at a pressure of 735.6 torr. If it occupies a volume of 0.45 kiloliters, what is its temperature? So this problem has lots of stuff in it. So let's go through for a minute and let's see what is important, right? So I'm going to go through a sample of gas that contains 12.5 moles. That's a number, so it's important. The pressure is 735 torr. It's got a volume of 0.45 kiloliters, and I want to know its temperature. So automatically, I'm thinking this is one instance of time. PV equals nRT. I've got to go through and look at my problem and be a detective and figure out what all of those variables are if given my problem. So I know I've got a torr, which is the pressure. I've got a volume of 0.45 kiloliters. I've got a number of moles. I know what R is, and I'm asked to solve for T. So I've got each of these pieces. I've just got to make sure that they are in the right unit. So that problem, even though it was lots of scary words and numbers, when we break it down and look at it from a math standpoint, a relationship standpoint, we know my pressure was 735.6 torr. I want to convert that into atmospheres because that's what my unit on R is. If I look, 1 atmosphere is 760 torr. So I can make a conversion factor with torr on the bottom, since that's what I'm trying to cancel out. And I'm left with 0.967 atmospheres. Volume is the same way. It's easy to convert from kiloliters to liters. We just move our decimal point over, right? Kiloliters is a bigger unit, so our number of liters from a really small kiloliter is going to be bigger. So we move our decimal point 3 places that way. So 450 liters is the same as 0.45 kiloliters. That's our volume. We don't have to change anything to our number of moles because our number of moles is already moles, right? And then our gas constant is 0.0821. That's given to us, and we don't know our temperature. But since we have all of our pieces in the right unit, all we have to do is do the algebra. And you can see I made a really common mistake here. I did this problem once, and then I X'd it out. I got to the end, and I got a huge, huge number for my temperature. I said, that doesn't sound right. Can you guys see my mistake? I used my pressure in torr, not in atmospheres. And that made my number super duper big for my answer. So that was that. Once I got to the end, I was like, hey, this doesn't seem right. I went back and checked my work and I found my mistake. So here is the actual work. Now you can see we took our pressure, 0.96 torr, times our volume, 450 liter, or sorry, I think I told you guys that wrong. Yeah, liters, from kiloliters into liters. That's equal to our number of moles times R times T. Then we just have to simplify it by doing some division to get T by itself. And our temperature should be somewhere around 424.5 Kelvin. Now, your problem, if it had asked you to find that in degrees Celsius, that's not hard. We just have to subtract away 273. Right? Questions? These problems aren't that difficult if you understand how to be a detective and find all the pieces from your problem, right? They're just a little persnickety because you got to make sure that your units are how they need to be. Okay, so the next thing we've got to talk about with ideal gases is our favorite stoichiometry. So obviously, right up until now, we haven't really talked about gases in terms of stoichiometry problems, in terms of big chemical reactions. And stoichiometry is never going to go away, right? When we learned it, I told you guys we're going to be doing it forever. Hopefully, it's gotten a lot less scary for you because we're adding another tool to our toolbox. So at standard temperature and pressure, we have this awesome conversion factor. We know that if a gas, you guys can see that. Light is being weird. Really need to learn how to do professional lighting. At STP, 1 mole of gas will always occupy 22.4 liters. That is regardless of the size of the particle, regardless of the polarity of the molecule. It is just a magic constant, right? So 6.02 times 10 to the 23rd particles will always occupy 22.4 liters at standard temperature and pressure. So at 1 atmosphere of pressure and 0 degrees Celsius, or 237 K, we can know based on the volume of that gas exactly how many particles of gas are in that container. Right? Just like we know if we're given a gram, we can convert that into the number of moles. If we're given a volume and we're at STP, we can convert that into a number of moles. So this is going to be another tool in our toolbox that will allow us to predict in a chemical reaction if I have 100 liters of this gas and I react it with a gram of something else, how much of a product am I going to get, right? So it's just going to be used as a conversion tool for us when we do our stoichiometry problems, right? So don't let that scare you when we just add that tool to all the tools that we already have. right? So at STP, we can use volume just like grams in a stoichiometry problem. Yay! So let's do one so you guys can get some practice with that. So this is concept check question 8 that we're going to be doing. So look at it at your along in your book if you can't see it on my screen. It is on page 306 of your textbook. So I've written it out here so I can go through and show you guys that strategy again of kind of looking at what's important and finding what's important in your word problem. Because like I said, understanding your problem is half the battle. Right? A chemist is making ammonia gas according to the following equation. N2 gas plus H2 gas makes NH3 gas. And we're given our coefficients there. They balance the equation for us already. We don't have to do any work with that. If she starts with 150 liters of nitrogen gas and an excess of H2 at STP, what volume of NH3 will be made at STP? So we've got some important stuff to note here. So in this problem, we see from my equation that everything is a gas. When everything is a gas and it's at STP, we don't have to do full stoichiometry because our volumes behave just like moles because of Avogadro's constant. That's why it's so important. So we don't have to do any stoichiometry at all except looking at our molar ratios. So we can go straight from volume of one gas to volume of another gas as long as we know our recipe, right? So for this problem, the only things that are important are the 150 liters of N2 and the volume of NH3. That's the only thing that I have to concern myself with it. I've got to look at how to do that math. So according to this recipe, this chemical equation, if we look here, that makes the lighting a lot better. Okay. NH2 to 3H2 make 2NH3. So if I start out with 150 liters of N2, I can use, since they're all gases and it's an STP, their volumes are just like moles, right? So I don't have to convert to moles. I can just assume they're moles, right? I can go straight from liters of one thing to liters of another using my coefficients, just like I could in stoichiometry, go from moles of one thing to moles of another. The only caveat there, and don't use this trick on every single problem because you're going to be wrong. It only works when we're dealing with nothing but gases. So when each part of our chemical equation is a gas, you can use this. And it's at STP. If it's not 1 atmosphere of pressure and 0 degrees Celsius, you can't use it. It's a special case. So help me build my math right here. So we're looking, I've got 150 liters of N2. What numbers am I going to put here in my conversion factor to go from liters of N2 into liters of NH3? What numbers do you guys think I need to put on that fraction?
Two over 1.
Why do you say 2 over 1?
Because in the equation, there's a 2 in front of the NH3, and there's not one.
Very good. So there's nothing over in front of our N2. So we assume that it's a 1 because it is. So 2 over 1. So 150 liters of N2, according to this problem, is going to produce twice as much ammonia. So our answer would be 300 liters. Easy, right? We're just adding another layer, right? So this is best case scenario. It's the most simple when it's this way. We're going to see in our next problem that it's not always that simple, right? Okay, so concept check question 8. Did we just do 8? Yeah, we did today. Sorry. I put it in my wrong stack of papers. Concept check question 9. So question number 9 uses just about everything we've learned so far in our study of chemistry, all the math, right? So hang with me. I'm going to try to teach you guys a couple of strategies for how you solve a big giant problem like this, and double check yourself to make sure you haven't made any mistakes. So this is our problem. It's concept check question 9 from page 306. A chemist is making hydrogen gas by reacting zinc and hydrochloric acid. We can see the chemical equation here. We've got a solid reacting with aqueous hydrochloric acid. We're making a aqueous solution, so we're making some ions, and a gas is going to bubble out of this solution. I know that because of the little parentheses in my chemical equation, right? So I notice off the bat, I've got a solid and an aqueous. I've only got one gas. So the strategy I used in my last question with the inert gases and not having to do stoichiometry and just going straight from volume to volume, I can't use that in this problem because I don't have gases, right? I've got, right? So, okay. So we're told that our chemist has excess zinc and 850 milliliters of a 5 molar acid solution. So 5 big M HCl. Remember that big M is molarity. So that's telling us how concentrated the solution is. And remember, molarity is moles per liter. We want to know at the end what volume of H2 will be made at STP. Holy cow, that's a lot of information, right? So we want to kind of map out this problem. Let's go through, and I'm going to underline my important things. So the 850 milliliters in the 5 molar solution is important. We know a volume, that we want to know volume of H2. So if I look, I'm going to underline my pieces. So I'm going to use up all of my hydrochloric acid, and I'm going to produce my H2. If I look at, one is a aqueous solution and one is a gas, right? So I don't have to worry about anything else because it's all in excess. So I'm going to map out in my head how I'm going to do this problem. Okay. Since we're going from one substance into another substance, I know that this is a stoichiometry problem, right? So we've learned stoichiometry problems up until now. We had to go from grams to moles, moles to moles, then moles to grams, right? We've got to kind of track it. So I'm going to map this problem out. I'm not given a mole to begin with. I'm giving a liters, right? But since it is an aqueous solution and I'm given the molarity and the volume, I'm going to be able to use that molarity to convert my liter of solution into moles of HCl, right? So we learned this last chapter. So now it's a tool in our toolkit. So I'm going to go from liters to moles. That's going to be my first step. Then, since I'm already in moles, I have my balanced chemical equation. I'm going to use my molar ratio to go from moles of HCl into moles of hydrogen gas. I can do that. I know how to do that. That's easy, right? We've learned that and done it several times. So moles to moles, easy because I got my recipe. That's my second step. Then I want to go from moles of H2 into what the problem asked me, the volume of H2. This is a new skill that we're learning because this is the gas part, right? This was our solution part. Now this is our gas part. And there are 2 ways you can do this problem. I'm going to show you the way that I think will be most applicable for you if you study chemistry any further. And that is going to be using our Avogadro's constant. So at STP, which this is at STP, I know if I know the number of moles, I know what volume that's going to be because at 1 mole of a gas is going to take up 22.4 liters, right? So you can use that as a conversion tool, just like our molar mass is a conversion tool. If we were going from grams to moles, we can use that same thing over here if we're at STP and we've got moles of a gas and volume of a gas. 1 mole of that gas is going to be 22.4 liters. If I've got 2 moles, that's going to be 44.4 liters, or 44.8. Sorry, I did that in my head. Anyways, if we were not at STP, right? If you were to look at the answer in the book that books gives for this, they don't use this trick. And I think that's an injustice, because this will get you, this is a lot easier than having to do a whole ideal gas law problem, right? So if we're at STP, we can use that 22.4 as a bridge. If we're not at STP, we have to do the ideal gas law to find what that volume is going to be, right? Since we'd be given all these other things, that just adds another layer of math to the problem. So just be aware that you can use this trick. And if we're not at STP, you got to do the ideal gas law to find your pressure, or sorry, to find your volume. Okay. So now, see how I mapped out that problem? I haven't done any math here. I've just done the thinking of knowing, okay, I know I'm going to have to go from here to here. I'm kind of thinking through what tools I'm going to need to find for my problem to allow me to be able to do those steps, right? So to me, it's easier to map it out, because then I can double check myself too as I do my steps to make sure that I'm not making any little careless errors that are going to ruin my answer down the way. Okay, so first step is going to be to go from liters into moles using my molarity. Okay, so let's look at this one. So any questions on how I mapped it out? I know you guys, I've been doing this a while, so sometimes it's easy for me to see how the problem works out. That's a skill that you guys are building right now, right? Working these problems and a tool. So hopefully the more we do it, the easier it will get for you to map out this problem, right? Your units can be your guide. So if you do kind of get lost, let your units be your kind of clue for what you're going to need to do and do it. So let's look at each of my steps. So my first step here, I'm going to show you guys. I am going to take my volume and I'm going to convert it using its molarity into moles of HCl. So if you look here, I got the 850 milliliters. My first thing was to convert that into liters because of the big M. Big M is moles per liter. So I've got to have my initial volume in liters for me to be able to do this part of the step over here. So this 5, I didn't just pull that out of the air. That's from my 5 big M solution. Is that 5 solutions really concentrated? There are 5 moles of acid in every 1 liter of solution, right? So it's just dimensional analysis. I'm just doing my math, using my conversion factors to make the unit that I'm in cancel out, and the unit that I want to be in, what I'm left with, right? So bam, bam, bam. 850 milliliters of this 5 molar solution ends up with 4.25 moles of acid. That's my first step. If I'm looking at my map, I just did this first part. I just converted from liters into moles. Now my next step would be convert from moles of acid into moles of gas. That's easy. These numbers, once again, I didn't just pull them from the air. They came from my molar ratio and my balanced chemical equation. My balanced chemical equation told me, we're looking back at it, that for every 2 moles of acid, I get 1 mole of gas. So 2 moles of acid, 1 mole of gas. So in the end, if I start out with 4.25 moles of acid, I'm going to end up with half of that, 2.125 moles of my gas. Okay, questions so far before I go to the third step? Looking back at my roadmap, since we've already done a whole lot of math and our brains already hurt, I've made the roadmap so I don't have to get lost in all that thinking. My last step over here is going to be to go from moles of my gas, which I'm already in, into volume of that gas. So I look back at the problem. I'm at STP. So whew, all I have to do is use my Avogadro's gas constant, or that relationship, that 1 mole of gas at STP occupies 22.4 liters. I don't have to do PV equals nRT, although I could, right? But I'm not. So this is our Avogadro's gas constant at STP. 1 mole of any gas occupies 22.4 liters of space. So over here, I have 2.125 moles of gas. So I want to cancel out that moles, and I want to figure out how much space that's going to take up. So 1 mole of gas is 22.4 liters. I put the mole on the bottom because that's what I'm trying to cancel. I got the liters on the top because that's what I want. And then that becomes a pretty simple calculation. My answer should be somewhere in the terms of 47.6 liters. Now, if you did this problem and you followed along and you checked yourself with the answer key at the end of the chapter, he gets a different answer. He gets 49. But that is very close to my answer. He also uses the PV equals nRT, right? He rounds every step of the problem, right? We didn't round to that degree, so our answer is actually more accurate than the books, right? So, food for thought if you are going to work these problems again and check yourself with the book. I showed you just a different way, right? So, questions about that? Good. Hopefully, I am going to post this video later this afternoon. So if you are working some of the review problems and you need a little bit of extra help, it's there for you. So the next section of the textbook talks about partial pressure, right? That's pretty easy. That's just saying if we have a mixture of gases, that our total pressure is just all those individual pressures combined, right? We also talk about a mole fraction. And a mole fraction is just that. It's a fraction, right? A part per whole. Just like almost every single ratio we talked about in our study of chemistry, right? The piece over the whole thing, right? So that could be the mole of an individual gas over the total moles, or it could be the pressure of an individual gas over the pressure of the whole thing, right? Those are two kind of ways to talk about this mole fraction. And practically for us, we're gonna use that in problems that have to do with mixtures of gases, or reactions that happen over water, because water is gonna have some vapor in there. So if we collect a gas that comes out of a solution, that gas is not gonna be pure. We have to subtract out the vapor of that liquid in there to get our actual answer. And there's a problem like that, the last problem in your review for this chapter. Just be aware that that's probably the most difficult one in this whole thing. So we're going to look at the last one we're going to work together is our comprehension check 10. So if you're looking at it, we've got a mixture of gases. In a mixture of two gases, the partial pressure of oxygen is 341 torr. The partial pressure of nitrogen is 761 torr. If there are a total of 6.78 moles of gas, how many moles of oxygen and how many moles of nitrogen are present in that sample, right? So we want to know if our pressure of oxygen is 341 torr, our pressure of nitrogen is 761 torr. We've got this many moles in our vat. We want to determine how many individual particles or number of moles of each one of those are in there. So we don't know the N for oxygen, which is our number of moles, and we don't know our number of moles for nitrogen, right? So I see some of these variables. We've been talking about ideal gas law, pressure, volume, temperature. This one uses mole fraction. So I'm looking here, it's a mixture. So anytime I'm dealing with a mixture, I've got to look at the individual parts of that mixture. So I know that our mole fraction can be moles of thing over total moles, or pressure of thing over total pressure. So my question for you guys in this problem, what pieces do we have? What piece did our problem give us? It gave us the total moles, and it gave us the partial pressures of each gas. So we have a piece from this guy, a piece from this guy. How can we use those pieces to find out the moles of each individual one? This is the part that I'm trying to solve for, right? I know this, and I know that. I don't know the bottom ones. So this problem is difficult because we're trying to smush both of these things together. But both of these equal our same thing. So in a way, we're using algebra here. If you are doing algebra and you've talked about substitution, this is a fancy way to apply substitution from algebra into one of these chemistry problems or into this kind of data analysis. So we know we can solve for our mole fraction of each piece. So I know the partial pressure of each one of these things. Our mole fraction is just the pressure of one over the pressure of all. I know the pressure of both of them. So I can add to find my total pressure. So I can solve for my mole fraction of oxygen and my mole fraction of nitrogen quite easily, right? 341 torrs for my oxygen. The whole thing is 1102 because 761 plus 341 makes that. So my mole fraction of oxygen is 0.31. My mole fraction of nitrogen is found the same way. Its piece is 761 over the whole thing is 0.69. This, once again, is just a ratio of a part to a whole. We've seen so many of these ratios, so many of these comparing throughout our study of chemistry this year, right? So we're taking a part over the whole thing. So this is essentially its grade. So our nitrogen represents 69% of that mixture. Our oxygen is 31%. Just like with any percentage, any pie that we're dividing things up into, any fraction, they add up to be these numbers should add up to be 100. If they don't, you did something wrong. Ours add up to be 100. Check. We did that part of the problem right. So that doesn't get us our answer. We want how many moles of these individual pieces are there. But we know that our mole fraction can be represented two different ways. Our mole fraction can be moles over total or pressure over total. So we just used our pressures to find our mole fraction. Now we know this, and we know our total moles, the problem gave that to us. So we can solve for our individual moles of each piece. And that's exactly how you solve this problem. So our mole fraction for O was 0.31. That equals our moles of oxygen over 6.78. Remember, I didn't just pull this number out of the air. It's our total moles that our problem gave me, right? And when I do that algebra, when I multiply both sides by 6.78, I get 2.1 moles of oxygen. I could subtract that from the 6.78, or I could do the math, do the algebra. Either way, you're going to get the same answer. And ideally, these two numbers should add up to be your total, just like our other two answers added up to be 100. Right? So, not that difficult of a problem once you know your pieces and get practice making your pieces, making your tools and the puzzle pieces come together to make the full picture. To me, in my study of gases, partial pressure and mole fraction are probably the hardest for me to wrap my head around, right? So just work through the problems, look back at this if you need it, and please shoot me a message or whatever if you need to see some of these problems or any problems from the review worked out in class on Thursday, okay? So what questions about concepts in this chapter do you guys have, if any? We've been going a little over an hour. I know it was a whole lot of math, but are there just any burning questions off the top of your head that we can address here in the next little while that you want to talk about? If there's nothing else, I'm really tired of talking. So I will see you guys on Thursday. We are going to do a version of the lab that's at the end of this chapter. So look forward to that. It should be pretty fun, if it works. So we will do that and talk about the work you guys did in the week that I was out. So your test for this chapter will be live this afternoon as soon as I finish a couple of the problems. And it will be for you guys to take tomorrow or Thursday. So be looking out for that. And I will see you guys in class on Thursday. Bye.